In this video, we want to take a look at the general procedure for how you do partial fractions. I want to point out that there's a theorem that says that every polynomial that has real coefficients can be factored into factors with real coefficients, and those factors are either linear or quadratic. So every polynomial with real coefficients can be factored into linear and quadratic factors. With real coefficients. Now, that doesn't mean we can easily find the factors, but this is the theorem. I believe it's the theorem of Gauss. Anyway, from our point of view, when we're looking at our polynomial p of x divided by some other polynomial q of x, I know that I can factor that into p of x times a bunch of factors down here, right? Whatever it takes to factor q of x. And those factors are either linear, maybe you got a couple of linear ones, and you got maybe a quadratic one, whatever. You won't have cubics, you won't have fourth degrees, you can always get it down to linears and quadratics. Okay? So that makes it so that the procedure that we're looking at for this partial fractions just have to deal with linear and quadratics. I don't have to deal with the other ones. So there are several situations, essentially three situations we find ourselves in. One, that all the factors are distinct linear. All the factors are linear and distinct. By that I mean the factors are all different from each other. Distinct. Two, they might be all linear but not distinct. Might be some factors the same. You might have one of the factors squared or cubed or something like that. All factors linear but some the same. And three, you might have some quadratic factors, some unfactorable quadratics. Unfactorable quadratics. Okay. We've already seen a couple of examples of the first one. Essentially, case one here, if you've got something like p of x over ax plus b, cx plus d, let's say ex plus f, then you're going to split that up into, in this case, because there's three factors, it'll be a sum of three things. You use your three factors on the bottom as your three denominators. And you just use constants on the top. Okay. And we've seen a couple of examples of that already, so I'm not going to do another one here. Two, if you've got some factors that are the same. So for instance, if you had p of x over ax plus b squared, then I'm going to write that as, see, it doesn't make much sense to do this, because if I need a common denominator between those two, it is just those two. I mean, it's just one of them. I already have a common denominator. So what we do is we square one of those, and then we give constants on the top. I want to point out that by doing this, now the least common denominator between these two is this one over here, right? And that in order to get these two fractions combined, I would have to multiply this one top and bottom by this ax plus b, which means my numerator now would be this capital A times ax plus b, but that would be a linear numerator. Remember that we're always insisting that the numerator have a smaller power than the denominator. So with this being quadratic, this would have to be only linear. And so when I look at what happens when I combine these two together, I'll get that common denominator, which is that one we wanted, and I will generate a linear numerator from this, because this will get multiplied top and bottom by this ax plus b. If I had that to a higher power, if I had, p of x to the ax plus b to the 7th power, well, I would use ax plus b. I'd use, come on now, ax plus b squared plus ax plus b cubed plus, and I just keep going until I got to ax plus b to the 7th power. My computer seems to be running a little slow at the moment. And I'd use a, b, c, d, e, f, and I think g would be the last one here for my constants on top. That is, whatever power you have here, use it to the 1st power, the 2nd power, the 3rd power, and the denominator. Notice that when you integrate these things, right, that if I'm looking at the integral, and the whole reason we're doing this is to break this up so we can integrate it. If I'm looking at the integral of a over ax plus b dx, then I've got a u substitution with u equals little ax, no, just little a, sorry, here we go, little a dx. What just happened? Think. U is the denominator. U equals ax plus b. Du is just little a dx. And so that integral becomes the integral. I got a u on the bottom. I've got a capital A on the top, but I'm going to end up with a 1 over a, 1 over little a. So I have capital A divided by little a times du. So I've got a divided by little a times the natural log of the absolute value of u, but u is ax plus b plus a constant. On the other hand, if I had an integral of something other than that linear one, so if I've got the ax plus b squared, be careful here, there's it's not a log. We get so used to come up with logs on these things, they think, this is just going to be a log of ax plus b squared. But no, that when you've got a u to the negative 2 power, because again, it's going to be u equal ax plus b, whatever that factor is, then du is a dx. So you end up with the b over a, and this is equal to b over little a, times the integral of 1 over u squared du. Well, to integrate 1 over u squared, that's a u to the minus 2 power, right? Sorry, this is b over a. This is u to the minus 2 power du. So that integrates to u to the minus 1 power divided by minus 1. So that ends up being minus b over a times 1 over ax plus b to the 1st power in the denominator, right? That minus 2 exponent becomes a minus 1 exponent. So don't get too carried away with your logs. That's only when you've got something. It's only when it turns into an integral of 1 over u. 1 over u squared is different. If I went all the way up to here, you'd have a 1 over u to the 7th power, and that would integrate to a u to the negative 6th power, right? Divided by negative 6. So there's that. Let's do one example of that, and we'll get back to the quadratic ones in the next video. So let's actually move down here to the page break, and let's do the integral of something like, I'm going to mix it up a little bit and say x squared times x minus 1 dx. And let's just put a x plus 1 on the top. Okay. So this one actually has got a combination of things. When I look at this x plus 1 over x squared plus x, minus 1, that it has 3 factors in the bottom. It has an x, it has another x, and it has that x minus 1. So when you have that repeated x and x, then I need an x and an x squared here. And then I'm also going to need an x minus 1 in the denominator. A, B, C. Notice, although this is quadratic, it's accompanied with this one, in that combining these two together, you multiply this one top and bottom by x, you've got ax plus b over the quadratic x squared. So that's all right. But it's going to be easier to integrate it this way with the a over x and the b over x squared. And then I need that factor of the x minus 1 there. So multiplying both sides by this common denominator, I've got that x plus 1 needs to equal this times the first fraction. One of the x's cancels out. So a times x minus 1. This, the x squareds cancel out, so I've got b times x minus 1. And then the last one, this x minus 1s, this times that, the x minus 1s cancel out, leaving just cx squared. Okay. To find a, b, and c, I'm going to plug in values for x. In fact, I'm going to plug in x equals 0. Over here I get a 1. Over here that's a 0 plus negative b, right? B times negative 1, and then that's plus 0. So that tells me that b is equal to negative 1. I'm going to plug in x equals 1. So this tells me that 2 is equal to a times 1 times 0. That's still 0. B times 0 is 0. And I've got c times 1. So that must be c times 1 squared there. So that tells me that c equals 2. I got to just plug in one more. I plugged in 0. I plugged in 1. You know, pick your next favorite number. I think I'm going to plug in minus 1. Let x equal minus 1. So this would be a 0 on this side. This would be a times negative 1 times negative 2, because the minus 1, minus 1. Then I have plus b, but I already know that b is negative 1, times, I'm plugging in a minus 1 for x, so this is also minus 2, plus c, but I know that c is 2, and then the x squared, so the minus 1 squared. So now I've got 0 equals 2a plus 2 plus 2 more. So negative 4 equals 2a, tells me that a is equal to negative 2. So my original fraction, where was it? X plus 1 over x squared times x minus 1 is equal to a, negative 2 over x, plus b, negative 1 over x squared, plus c, 2 over x minus 1. So if I wanted to integrate this thing, dx, it would be the same as integrating all of this thing, dx. This integrates to negative 2 natural log absolute value of x. This integrates to, this is an x to the negative 2. So it integrates x to the negative 1 over negative 1, but there's already a minus 1 there, so that's just 1 over x. And then this thing with the u equal that denominator, that's going to be 1 over u du, not equals plus 2 times the natural log of the absolute value of x minus 1 plus a constant. Okay, so there was a couple things there. I had some distinct factors and I had some of the same factors. I had, you know, the x minus 1 was different than the x, but there's 2 factors of x here, so I had to break it up that way. All right, in the next video we'll look at what you do with unfactorable quadratics.